Alright, welcome to Balancing Chemical Equations, a Dr. Kelly reaction. The best way to talk about chemical reactions is to start by conducting one. But I believe in two first, so I'm not just going to conduct one, I'm going to conduct two of my favorite chemical reactions. First, I'm going to take some calcium carbide and I'm going to place it in a jack-o'-lantern. Into that calcium carbide in my jack-o'-lantern, I'm going to add some water. Water and calcium carbide react to produce acetylene gas and calcium hydroxide aqueous. Now, acetylene gas, if you're unfamiliar with it, it is highly flammable. And it reacts with oxygen to form carbon dioxide and water. Let's observe.
Okay, this is a classic goodie. It's the generation of acetylene gas and then the ignition.
So you can see chemical reactions can be very dramatic and very entertaining and a great way to celebrate Halloween. So let's take a look at the reactions behind this. This may or may not be, depending on the course sequence, the first time you've encountered a chemical reaction. Chemical reactions are written with a certain style and in a certain way to communicate information. If we take a look at our first reaction here, it gives us a lot to talk about. A lot of different things we can discuss. So let's look at our first reaction. Our first reaction, and I'm going to try to write it a little bit neater here, says that we have calcium carbide solid reacting with water. Just a second, I'm going to write it just a little bit neater here. Ideally, I'd write it in one line, but I think if I do that, I'm going to wind up writing it too small and too sloppy for you to be able to tell anything. All right. Let's take a look at this pink reaction here that I've rewritten, and let's read it. The first thing we need to do when we encounter a chemical reaction is be able to read it. So we need to introduce some terminology to you for the first time. 1 formula unit of calcium carbide solid reacts with 2 molecules of water to yield 1 molecule of acetylene gas and 1 formula unit of calcium hydroxide aqueous. First, let's deal with the plus signs. In a chemical reaction, let's actually do the two parts of a chemical reaction here. Everything on the left-hand side of an arrow is referred to as a reactant. The left-hand side of the arrow is where you find your reactants. The right-hand side of the arrow, the compounds on that side of the arrow, we refer to as products. So we've got reactants here, reactants, and then we have products over here. When we're reading our chemical equation on the reactant side and we come to a plus sign, see we have a plus sign here, plus sign. On the reactant side of our arrow, on the reactant side of the arrow, we call this plus sign, or pronounce this plus sign, reacts with. So if I'm reading the chemical equation, I say reacts with. So I say calcium carbide, 1 formula unit of calcium carbide solid reacts with 2 molecules of water to yield, the arrow in a chemical equation is pronounced to yield. You'll also see it pronounced to produce. It functions like an equal sign in math class. You can treat the arrow in a chemical reaction just like you can the equal sign in a math class. In a math class, things on both sides of that equal sign have to be equal to each other. In a chemical reaction, because matter can't be created or destroyed, the substances on both sides of that arrow have to be equal. And that's going to be the subject of today's lecture, but I'm getting ahead of myself. On the other side of the yield sign, when I encounter a plus sign, and that's a plus sign, I pronounce the plus sign and. I just use the word and for it. Another thing you'll notice when I read this chemical reaction is I said that I had one formula unit of calcium carbide solid. You'll notice that every substance in this chemical equation has parentheses next to it with a lowercase cursive letter. These lowercase cursive letters denote phase. There are 4 phases that you're responsible for knowing and what their representations are. If something's a solid, we use a cursive lowercase s, solid, and my cursive s looks like that, which sometimes people think is an O, but that's a cursive letter S, solid. And then, guess what phase the letter L represents? If you said liquid, then you're right. You can pass chemistry already. Then we have G, and guess what G stands for? Oh, time's up. If you didn't say gas right away, you weren't paying attention to me. The last phase that may be new to you, but you've probably seen by this point in the semester, is AQ. AQ stands for aqueous, which means that the substance you're looking at is dissolved in water. These are the 4 most common phases. Now, there are lots of other phases. Common one that you'll see is sometimes you'll see the abbreviation XE in parentheses for dissolved in hexane, or I've seen BEN for dissolved in benzene. So you'll see different phases out there, but you're only responsible for knowing solid, liquid, and gas. So you can see that your calcium carbide here is a solid because it has an S next to it. We can see that our water is a liquid because it has an L next to it. We can see that acetylene here is a gas because it has a G next to it. And calcium carbide's aqueous because it has that AQ in parentheses next to it. So that's how you denote phases in a chemical reaction. And phases are going to make a big difference when we begin considering the energy that different substances possess. And for ionic compounds, it makes a difference as to the physical properties of that substance, how it physically exists. Let's also look at the 2. There is a 2 in front of my water. What is this 2 here? A big number out in front of a substance in a chemical equation is referred to as a coefficient. And a coefficient is a big number out in front of a chemical species in a chemical equation. What that coefficient tells you is the coefficient tells you it tells you the number of the species needed to carry out the reaction. Another way of thinking of it is another way of thinking of these coefficients here is that a coefficient gives you the ratio of the species in the problem. In other words, we can think of this 2 here as telling me that I need 2 molecules of water for every 1 molecule calcium carbide I have. Or another way of thinking of it is, to carry out this chemical reaction, I need 2 moles of water for every 1 mole of calcium carbide. What's a mole? Depending on your lecture sequence, you may or may not have gotten to that yet. You can think of it as, for every 1 formula unit of this you have, you need 2 molecules of water in order to carry out the chemical reaction. And that's what your coefficients tell us. The subject and object of today's lecture is for you to be able to place those coefficients in a chemical equation yourself. Why do we put these coefficients there, and where do they come from? They come from the law of conservation of mass. Coefficients are what allow us to obey the law of conservation of mass. The law of conservation of mass says that matter can be neither created nor destroyed by normal chemical means. In the context of a chemical reaction, that means on each side of the arrow there must be the same number of each type of atom for a chemical reaction. Let's take a look at our reaction of calcium carbide with water. If we look at this reaction, cleaning things up a little bit here. On the reactant side, I have 1 atom of calcium. I have 2 atoms of calcium. I have 2 atoms of carbon. See, there's a little 2 there. So I have 2 atoms of carbon. I have 4 hydrogens. I have a little 2 there, and I have a big 2 there. So I have 4 atoms of hydrogen, because I'm multiplying that 2 times that 2. This 2 is in front of the water, so it applies to both atoms there. So not only do I have 4 hydrogens, but I have 2 oxygens. On this side of my arrow, I have 1 calcium. I have 2 carbons. I have 4 hydrogens. 2 there, and then there's a 2 in parentheses here, meaning I have 2 hydrogens there. And then my oxygens, I also have 2, because that oxygen's inside that parentheses with a little 2 there. So you can see how this chemical reaction obeys the law of conservation of mass. Because during this chemical reaction, I haven't created or destroyed any atoms. I've simply rearranged the atoms. So when we write a chemical equation, the chemical equation must be balanced. And by the term balanced, I mean it obeys the law of conservation of mass. The problem is, or the problem you're going to have here in a second, is that chemical equations aren't always written in balanced form. Most of the time, we observe a natural phenomenon, so we're able to determine what compounds are reacting and what compounds are being produced, but we then have to do some math in order to balance the chemical equation. Let's take a look at the second reaction we saw in our demonstration, the fun one, the one where it exploded. We were able to watch our exploding pumpkin video, and we were able to note that acetylene gas was reacting with oxygen gas to yield carbon dioxide, water, and we also saw very clearly it also produced some energy. But that's a discussion for another day. Right now, we want to see if the reaction, based on our observation, obeys the law of conservation of mass. We know acetylene and oxygen react, and we know we produce carbon dioxide and water. If I take an inventory of what I have, I see I have 2 carbons on the reactant side, I have 2 hydrogens on the reactant side, and I have 2 oxygens on the reactant side. On the product side, I have 1 carbon, I have 2 hydrogens, and I have 2 oxygens and carbon dioxide, and 1 oxygen and water. So I have 2 plus 1 is 3 oxygens. So does the reaction as I've written it obey the law of conservation of mass? No! It doesn't, does it? Did I wake you up? But at any rate, so we have to do what's known as balancing the chemical equation. Now we know for a fact, undeniable, that this reaction involves acetylene and oxygen. And we know it produces carbon dioxide and water. That means that I can't change the compounds reacting. I can't touch any of these little numbers here. I can't touch the numbers in my compounds. The only thing I can do is change the number of molecules that react. I can't touch what the molecules are. I can only balance my chemical equation by putting numbers in front of the compounds in my chemical equation. So let's see what we can do to balance this chemical equation. When balancing chemical equation, it's a good idea to save for last any compound that appears by, any element that appears by itself. If we look at our chemical equation here, notice oxygen, the element oxygen, appears on this side of the equation by itself. So I'm going to balance it last. So I'm going to start off by balancing carbon. I have 2 carbons over here. I only have 1 over here. So I have to ask myself, what can I multiply 1 by to get 2? Everybody get out your calculators. No, right? 1 times 2 is 2. So I need to multiply my carbons on this side of my equation by 2. So I place a 2 out in front of the compound that contains carbon, carbon dioxide. What that does is that gives me 2 carbons now, but in changing my carbon content, it also changed my oxygen. Instead of having 3 oxygens, I now have 2 times 2 is 4, plus 1 from the water. Hi, I'm an oxygen here, don't forget about me. To give me 5 oxygens. So now I'm looking at my chemical equation, and I see that my hydrogens are balanced. I have 2 hydrogens on both sides of my equation. So they're good, they're happy, they're getting along. So that leaves me with my oxygens. I have 2 oxygens on this side of my equation. I have 5 oxygens on this side of my equation. Always treat this as a mathematical problem. Don't make it too difficult. Just ask yourself a very, very, very easy question. What can I multiply the lower number by to get the higher number? So I'm going to ask myself, what can I multiply 2 by to get 5? In other words, 2 times x equals 5, so x must be 5 halves. So that's what I need to multiply 2 by to get 5. So I have my answer, so I'm going to place 5 halves in my chemical equation. So I have 5 halves there in my chemical equation. That, because I'm multiplying 5 halves by 2 there, that means I now have 5 oxygens on this side of the equation. So now I check. 2 carbons here, 2 carbons there. 2 hydrogens here, 2 hydrogens here. 5 oxygens here, 5 oxygens there. My equation is now balanced. If I was working in thermochemistry, I'd be done right now. However, when I'm not working in thermochemistry or thermodynamics, I have an ideological issue. Let's read what we've written here. 1 molecule of acetylene reacts with 5 halves of a molecule of oxygen to yield 2 molecules of carbon dioxide and 1 molecule of water. Let's read that again. Really? Do we have to read it? Yes, I have to read it again. 1 molecule of acetylene reacts with 5 halves a molecule of water. By definition, what's a molecule? A molecule is the smallest unit of a compound. Can you have anything smaller than the smallest? No, you can't. Therefore, you can't have half of the smallest. This creates an ideological problem for us, right? Mathematically, we're fine, but ideologically, we're not. So what we want to do to make sure that the chemical reaction conforms to our dogma here is we want to clear the fraction. What's the easiest way to clear out a half? Multiply through by 2. So we're going to multiply the entire equation through by 2. And by that, I mean the numbers out in front. So 5 halves is going to become 5. Our 2 here is going to become a 4. And we're going to have a 2 in front of our water. If we were to write it all nice and clean here, and I know that's what everybody wants to do, then we would have 2 molecules of acetylene gas reacting with 5 molecules of oxygen gas to yield 4 molecules of carbon dioxide gas plus 2 molecules of water gas. We haven't unbalanced our equation. Feel free to take inventory if you want to. And we haven't changed any of the substance. And this is an example of balancing a chemical equation. If you didn't follow me that time, don't worry, we're going to work plenty of examples. Matter of fact, we're going to have more fun balancing chemical equation than you would waiting up for the Great Pumpkin. Why don't you write down the Great Pumpkin? I hope you write it down sincerely. Write down the Great Pumpkin. How to balance a chemical equation in 3 easy steps. First, never change the subscripts to balance a chemical equation. Only change the coefficients. 2, balance elements that are up here by themselves last. Apparently, I was feeling rather southern when I wrote that. Balance elements that appear by themselves last. Appear by themselves last. 3, avoid balancing atoms and polyatomic ions separately if possible. So let's take a look. Let's execute these 3 rules using several different examples, because one example is never quite enough. Perhaps the easiest reaction we could do is to make some table salt. Alright, I want to make some table salt, so I react sodium solid with chlorine gas. First thing I do is take inventory. And this is the step I see a lot of my face-to-face students not wanting to do. It's time-consuming, it's obvious. It's an accounting tool that will save you headaches in the long run. So, I take my inventory. I have 1 sodium atom over here. I have 2 chlorine atoms. On my other side of my arrow, I have one sodium atom and I have one chlorine atom. Alright, I look and I see, okay, I've got two elements that appear by themselves last, both sodium and chlorine, so it doesn't matter which I balance first. I look and I say, see, look, my sodium's balanced 1 to 1, but look at my chlorine. I have two chlorines over here. I only have one chlorine over here. So I ask myself, what can I multiply 1 by to get 2? What can I multiply 1 by to get 2? Well, duh, 2, right? I can't place a 2 in the center of my equation. That's a no-no, right? I have to place a 2 in front of a compound. So I have to have 2 not just of the chloride now, but I now have 2 of the sodium. So by balancing my chlorine, I unbalanced my sodium. And that's going to be a common theme here. All right, so my chlorides are balanced. Let's take a look at my sodium. I have 2 sodiums over here, 1 over here. What can I multiply 1 by to get 2? 2. So I place a 2 in front of my sodium, and that gives me 2 sodiums. And now I'm balanced. Chemistry's easy, life is hard, yes? Especially if you're Charlie Brown. Why don't you write down Charlie Brown? Everybody write down Charlie Brown. All right, let's take a look at another example here. We have aluminum reacting with hydrochloric acid to yield aluminum chloride and hydrogen gas. And I'm going to omit phases from this point forward in the discussion because I want to focus on balancing and I don't want people to lose the forests through the trees here, so I'm not writing any phases at the moment. All right, we have our equation. First thing we do is we take our inventory. I have 1 atom of aluminum on this side, 1 atom of hydrogen, and 1 atom of chlorine. On this side of the equation, I have 1 atom of aluminum, 3 atoms of chlorine, and 2 atoms of hydrogen. I want to balance elements that appear by themselves last. Aluminum and hydrogen appear by themselves. So I'm going to balance chlorine first. I have 3 chlorines, so I ask myself, what can I multiply 1 by to get 3? 3, right? 1 times 3 is 3. So I'm going to place a 3 in front of my molecule of hydrochloric acid, right? I have to put those subscripts in front of a molecule. I can't put them inside the molecule. And I can't change my numbers down here. I can't change my subscripts. I can only put numbers right here. So by placing that 3, that changes not just my number of chlorines, but it also changes my number of hydrogens. All right, so my chlorines are balanced. My aluminum is balanced. My hydrogens are not. And this is where taking a mathematical approach will benefit you. Ask yourself, what can I multiply the lower number to get the higher number? What can I multiply 2 by to get 3? Where do I get the 2 and the 3? There's the 3, there's the 2. So what can I multiply 2 by to get 3? 3 halves, right? So I place a 3 halves in front of my hydrogen, and what that does, uh-oh, 3 halves in front of, just a second guys, sorry, messed that up. So I place a 3 halves in front of my hydrogen, and when I do that, times 3 halves, that balances my hydrogens. So my hydrogens are balanced, my aluminums, and my chlorines are balanced, and my aluminums are balanced. So I have a balanced equation. If I was in thermochemistry, I'd be done. But remember, we don't like the ideological visual of having half of a molecule, because you can't have half of a smallest unit. So how are we going to get rid of that 2? We're going to multiply the entire equation through by 2. So that becomes a 2, that becomes a 6, 2, and 3/2 times 2 is 3. So there's our balanced equation. Ta-da! Or if I wanted to, let me just rewrite it for you home gamers. All right, there you go. As long as you're writing down the correct answer, why don't you also write down the word Linus? Everybody write down the word Linus. Linus. What? What's that you say? You want another example? All right. No need to beg. You talked me into it. We'll do another example. Let's take a look at the Hank Hill tribute reaction. The combustion of propane to form carbon dioxide and water. Take your inventory. 3 carbons, 8 hydrogens, 2 oxygens. On the other side, 1 carbon, 2 hydrogens, and I'm going to write my oxygens in such a way that it serves as a mnemonic device. I have 2 oxygens here, and I have 1 oxygen over here. So what I'm going to do is I'm going to write 2 plus 1 equals 3. And you're saying, Dr. Kelly, if you can't add 1 plus 2 in your head, you have issues. Yeah, I know that. But I want to remind myself when I'm doing the inventory that my oxygen is split between 2 molecules. And therefore I do this not because I need it for math, but so that I can remember, hey, Dr. Kelly, hey, you listening? Are you listening? Your oxygen's in 2 different compounds. So that's why I write that way. You may be smarter than I and have a memory like a steel vault, but I think this trick will help you out. All right, so let's begin working our way through reconciling our inventory. Notice oxygen appears by itself. So we're going to save oxygen for last. We're going to start off balancing our carbons. I have 3 carbons on one side, 1 on the other. What can I multiply 1 by to get 3? You guessed it, 3. So I multiply my carbon dioxide by 3. That not only gives me 3 carbons, but it changes my oxygen. I now have 3 times 2 is 6, plus 1 is 7 oxygens. All right, so my carbons are balanced. How about my hydrogens? I have 8 hydrogens here, and I have 2 hydrogens here. What can I multiply 2 by to get 8? What can I multiply 2 by to get 8? 4, yes? Everybody's shouting at me, 4, 4, 4. Sounds like a golf course in here. So we multiply 4 times 2 is 8. And we've got 3 times 2 is 6, plus 8 is 14. So we've got 14 oxygens now, and 8 hydrogens. So now if we look, we've got our carbons balanced, we have our hydrogens balanced, we just need to balance our oxygens. What can you multiply 2 times to get 14? 7, right? So now your carbons, hydrogens, and oxygens are balanced. And you're done! Chemistry's easy. Life is hard, yes? All right, let's take a look at a reaction that's a different spin than what we've been looking at up till now. Let's look at one that breaks the mold so that we know that we're blessed. That's a 3 there. And we're reacting with nitric acid. All right. And sodium nitrate. And I'm going to move that plus over just a little, those pluses over just a little bit so that we can do. Okay. So we've got a longer one than we're used to looking at, and it also gives us a chance to exercise number 3. Avoid balancing the atoms in a polyatomic ion separately if possible. This equation gives us the perfect example. We start off taking our inventory. I have 2 atoms of sodium. Then I have my sodium attached to my carbonate ion, CO3. I have the option of balancing the carbon separately and then the oxygen separately, or balancing it as a unit. I can only balance carbonate as a unit if I see the carbonate ion appearing on the other side of the equation. Is carbonate over here? No, carbonate is not over here on this side of the equation. Therefore, I can't balance carbonate as a polyatomic ion. I have to balance carbonate separately because it doesn't appear on the other side of the equation. So, I have 1 carbon and then my oxygen. Now I have 3 oxygens in my carbonate, but then I see another 3 oxygens over here. These 3 oxygens are part of the polyatomic ion nitrate. Before I count these oxygens separately, I want to see, does nitrate appear on the other side of my equation? It does, it does, it does! Since I have nitrate on both sides of my equation, I'm going to attempt to balance this equation by treating nitrate as a polyatomic ion, or by treating nitrate as a single unit. So I'm going to call my oxygen count 3, and then I'm going to say I have 1 nitrate. And then I still have to account for my hydrogen, so I have 1 hydrogen. On the other side of my equation, I have 1 sodium. Hi, I'm sodium. And then I have 1 carbon. Then for oxygen, I have 1 oxygen here, 2 oxygens here. These oxygens are part of nitrate, and I'm balancing nitrate as a single unit, so I'm not going to count those. So my oxygen count for this problem would be 1 plus 2 is 3. Then I have nitrate, and I'm treating nitrate as a single unit, so I'm going to say I have 1 nitrate. Then I have hydrogen, and I have 2 hydrogens on this side of the equation. Alright, so let's see what we've got balanced and what we don't. I have 2 nitrogens here, 1 nitrogen here. So what can I multiply? I'm sorry, nitrogens. I have 2 sodiums here, 1 sodium here. What can I multiply 1 by to get 2? 2! So I have to place a 2 out in front of my sodium nitrate. That changes not only my sodiums, but it also changes my nitrate count. Now I look over at my equation, and I see that the next thing that's not balanced is my nitrates. I have 2 nitrates here, only 1 nitrate here. So what can I multiply 1 by to get 2? 2! So I place a 2 out in front of my nitric acid, and that gives me 2 nitrates, and it gives me 2 hydrogens, which, hey, balances out my hydrogens, and boom, I'm done. I aced it, because I'm the man, and after all, I paid for every equation I ever balanced. All right. By this point, I think you know how to balance chemical equations. However, I want to see you do it. Well, I can't actually see you because you're on the other side of the computer. But what I want you to do is pause me, balance this chemical equation yourself, then unpause me to see if you got it right. No cheating. We're on the honor system here. All right. Did you pause me? Tell the truth. Some of you just kept on listening, didn't you? All right, let's go ahead and erase through this here. Take our inventory. I have 3 sodiums. On this side of the equation, I have the phosphate ion. I notice it's on the other side of the equation as well. So rather than break it up, I'm going to keep it together and try to treat it as a unit. So I've got 1 phosphate. Then I have 1 magnesium. Then I have 2 chlorines. On the other side of the arrow, I have 1 sodium, I have 2 phosphates because of the little 2 down there. Then I have 3 magnesiums. And then I have 1 chlorine. Nothing appears by itself, so I just need to plunge on in. I have 1 sodium on that side, 3 on the other side. What can I multiply 1 by to get 3? 3. So I place a 3 out in front of my sodium chloride, and that changes not just my sodium, but also my chloride. Then I have 1 phosphate on this side, 2 phosphates on the other side. What can I multiply 2 by to get 1? What can I multiply 1 by to get 2? 2. So I place a 2 out in front of there, and man, that undoes all my hard work, doesn't it? And that gives me 6 sodiums and 2 phosphates. But rather than go back and chase my tail right now, I'm going to keep pushing forward and see what happens. Maybe I get lucky. I've got 3 magnesiums right here, 1 magnesium's right here. What can I multiply 3 by to get 1? 3. When I do that, that gives me not only 3 magnesiums, but it changes my chlorine count to 6. All right, so we start back at the beginning again because we're still not balanced. Oh, we've never balanced our chlorines, actually. I have 6 chlorines over here, 3 over here. What can I multiply 3 by to get 6? 2, right? So I'm going to come up here, and I'm going to multiply my 3 coefficient by 2. So that makes that 3 a 6, and that changes my sodium to 6, and my chlorine to 6, and boom! Balanced! Dropping like the great pumpkin. Why don't you write down Marcy? Write down Marcy. M-A-R-C-I. Marcy spelled her name with an I. M-A-R-C-I. Marcy. All right. One last balancing equation for you to try. Again, I'm down on my hands and knees here. Please, please pause me and try to balance this yourself before looking at the answer. Did you pause me? I paused. I paused. Did you pause? I hope you paused. All right. By now you're looking at the right answer, and we're done. No. All right. Let's run through it real quickly. We take our inventory. We have 4 carbons, 10 hydrogens, 2 oxygens. All right. On this side, I've got 1 carbon, 2 hydrogens, and 2 plus 1 equals 3 oxygens. Save oxygen for last since it appears by itself. Let's start with our carbon. What can I multiply 1 by to get 4? 4. So I place a 4 in front of my carbon dioxide. That gives me 4 carbons, and 4 times 2 is 8, plus 1 is 9 oxygens. Now I want to balance my hydrogens. I have 2 on this side, 10 on the other. What can I multiply 2 by to get 10? 5. That gives me 10 hydrogens, and it changes my oxygen count. It gives me 8 plus 5 is 13 oxygens. I have 2 oxygens over here, 13 over here. What can I multiply 2 by to get 13? 13 halves. So I multiply my oxygen by 13 halves, and now I'm balanced. Mathematically, I'm balanced. If I was a pea chemist or working on thermodynamics, I'd be done. But I want to get rid of that ideological inconsistency of that 13 halves, so I'm going to multiply the entire equation by 2 to clear the halves. And you're done. That's it. See you in the next lecture. Beep.